Let's look at a few more examples of revolving around an axis where we're best using shells, the shell method, and then we'll look at some examples where we can't tell which method works and we have to think about that as well. So let's begin with something like this. Y equals ln x. So far we've looked at examples where we revolve around the y-axis. Well, let's actually look at one where we're moving around the x-axis. So we're going to go y equals ln of x, and we're going to go from y equals 0 up to y equals 5. And we would like this region here to go around the x-axis. So first, what happens when we do so? Again, we get this sort of a solid base. If we revolve this around the x-axis, we get a solid base with a bowl shape cut out of the middle. And now, what makes more sense here? The first question should always be, should we look at a horizontal line segment or a vertical line segment? If we were to look at a vertical line segment here, that's not the best choice. This vertical line segment, when we revolve around, doesn't really work best here because from here we have this straight line down to the curve ln of x, but over in this region it's a straight line to a straight line. Remember, anytime we have an option, we prefer not to have a situation where essentially we'd have to break it up into two different regions. And because here it's straight line to curve, and over here it's straight line to straight line, if we would like to use a vertical line segment in our revolution, we'd have to make two different regions. So instead, it makes more sense for this region to use a horizontal line segment that makes up our region. Because if we use a horizontal line segment, it goes from the y-axis up to ln of x, no matter where we make the horizontal line segment. Y-axis to ln of x, y-axis to ln of x, y-axis to ln of x, across the entire region. So that's really always your first question when doing these types of problems. Should I be using a horizontal line segment or a vertical line segment? And then everything else goes off of that. In this case, the horizontal line segment makes more sense. What happens when we revolve a horizontal line segment around the x-axis? If we take this horizontal line segment and revolve it around the x-axis, we get the cylinder type shape, which is exactly what shells are good for. So we're not using shells because we're revolving around the x-axis or because we're revolving around the y-axis. The axis that we're using to make the revolution doesn't play a role in whether it's shells or disc washer. What matters is whether we should be using a horizontal or a vertical line segment and how that plays when you make the revolution that is requested. In this case, we have a horizontal line segment because that makes sense for our region. Revolving it around the x-axis makes a cylinder, which means that we have shells. So this is a horizontal line segment around x-axis, and that makes a cylinder. So this is shells. Remember, our formula that we love for the shell method is the area of that cylinder, which is the circumference of the cylinder times the height of the cylinder. So that's 2 pi r, that's the circumference, multiplied by the height. So 2 pi rh is what we'd like to use as our formula here. Alright, so then we think, what is the variable? Well, the variable is, what do we have? We take our line segment, in which direction do we have to move the line segment in order to fill out the entire region? We have to move this line segment vertically, up and down. Right, so we have to change the y value. Changing the y value changes the line segment, so y is the variable. Right, so vertical movement to fill the region, which tells me that this is y is the variable. Alright, so if y is the variable, everything has to be in terms of y, which this is not in terms of y. X is the variable as written here. So we actually need to take this and solve it for the other variable. We need to solve for x. So we have y equals ln of x. That's the same thing as saying x is equal to e to the y. Remember, e to the y is x. So x is equal to e to the y. So I'm going to rewrite that as x is equal to e to the y. for my equation. X is equal to e to the y. This is y equals 0 to y equals 5. Those are both fine because those have the variable y equals to y equals. So those are going to be my limits of integration. So the limits of integration will be y equals 0 to y equals 5. Then we just need to think about how we make our formula. 2 pi RH is the area that we get. Then we're going to integrate that across the entire region. So we want 2 pi RH evaluated from 0 to 5, and that will fill out the entire region in question. 2 pi is fine. What is the radius? The radius of this cylinder is exactly where we are on the y-axis. This is the radius of the cylinder in question, and that is y. That's the variable y. 2 pi y. Right. So 2 pi RH. Y is the radius because that tells me how high up I have to move before I revolve around the x-axis. Finally, the height. The height is the function. This is the height of the cylinder, and the height of the cylinder is exactly how far out we go to reach the function. So that is the function e to the y. So 2 pi RH is 2 pi y e to the h. I'm sorry, e to the y. Y is our variable, so we're integrating with respect to y. And that is the integral. So just to recap here, again, whether we're using shells or disc washer, it doesn't depend on what we're revolving it around. It depends on what shape we're using, a vertical line segment or a horizontal line segment, and how that looks when we actually make the revolution. So we start by asking vertical or horizontal, then we make the revolution and ask what shape we get. If we end up getting a cylinder, it's shells. If we end up getting a disc or a washer, it's disc washer method. Let's look at another one. Let's take this region and rotate it around the x-axis. Y equals square root of x, x equals 3. So let's first ask, would I rather use a horizontal or a vertical line segment to fill this region out? And the answer to that question is, it actually doesn't matter in this particular shape. If I take a vertical line segment, then it's curve to x-axis, no matter where we go. Curve to x-axis, curve to x-axis. Across the entire region, we'll have curve to x-axis, and that's great. So a vertical line segment would be fine. If we would go with a horizontal line segment, then it's curve to the straight line x equals 3. Curve to x equals 3. Curve to x equals 3. No matter where we make our horizontal line segment, we get curve to x equals 3. So we can actually use either effectively in this method with just as much work. So let's stick with the one that we've been looking at for this section, which is going to end up being the cylinder, the shell method, and that's going to be a horizontal line segment. Because if I take a horizontal line segment, revolve it around the x-axis, I end up getting a cylinder. So let's use these horizontal line segments, which means that we end up getting a cylinder. If we take these horizontal line segments, rotate it around, then we end up getting this cylinder out of it. What does that mean? Because it's a horizontal line segment and we'd have to move it vertically to fill out the region, the vertical movement means that y is the variable, which means that we need everything in terms of y. Okay? So if we need everything in terms of y, what we need to do is we need to say, what are the limits of integration in terms of y? This is y equals 0, and this is whatever the y value is corresponding to x equals 3. Well, if y is square root of x, then this is y is equal to the square root of 3. And so that's going to be my upper limit of integration. Y to y, 0 to square root of 3. Second, we need all of our functions in terms of y being the variable, which means I need to rewrite this one as x is equal to y squared. Right, so we've got my function, we've got everything in terms of y, and since we are making a cylinder shape, we're looking at 2 pi RH as our formula. Integral from 0 to square root of 3, using y as the variable, so dy, 2 pi RH, 2 pi, radius, what's the radius? The radius in these cases is going to be whatever our variable is, because if I move up, this corresponds to some unknown value of y, which is the radius of the cylinder. So 2 pi y for the radius. And finally, what is the height of the cylinder? Now this is one where we have to be a little bit careful. The height of the cylinder is this distance here, which is not the function. If we would just look at x equals y squared, we end up getting this small, we get the axis up to the curve. That's the height if we have our heads turned on the side. What we actually want is that whole distance. So this whole distance right here, that's the height of the cylinder, but it's 3, the total distance of 3 out, minus the function. So this can be a little confusing. I'll go over it again. 3 minus y squared. Because this distance right here is 3, this distance right here is y squared, so the height of the cylinder, this horizontal line segment here, is 3 minus y squared. And that's our 2 pi, that's the r, that's the h, y is the variable, and we're done. Alright, let's look at another one. Okay, so this will combine a few things. We're going to ask what a horizontal or vertical line segment makes sense. Does that lead to disc washer or else shell? And have another complication that we saw in a previous example as well. Okay, so let's look at this. X is equal to y squared plus 1. We want this region right here. And we want to rotate it around the line x is equal to -3. That's our goal. Rotate this region all the way around the line x equals -3. So there's going to be a hole drilled out of the middle when we do that, because when we take this and we go all the way around, this sort of looks like a funnel shape or a curved cone shape, but there's nothing in the middle because all this stuff is not part of the rotation. There's nothing in this region right in here to rotate around. So that's our goal. The first question is always not, is this disc washer or shell? The first question is, should I be using a horizontal or a vertical line segment to fill out the region? Okay, so that's fine. Vertical does not make the most sense here. If we used a vertical line segment, I'd have straight line to axis, but over here I'd have straight line to curve. So we'd have to use two different regions if we wanted to use a vertical line segment. What happens if we look at horizontal? If we look at a horizontal line segment, then we have axis to curve, axis to curve, axis to curve. Anywhere we look, a horizontal line segment makes axis to curve. So, horizontal makes sense. Notice that I didn't say anything about disc washer or shell. All I said is, what segment should I use? Horizontal or vertical? And based on the region, I want to use a horizontal line segment. Next I say, what happens if I take a horizontal line segment and rotate it around this vertical line? this vertical line x equals -3. When I take a segment like this and rotate it around x equals -3, I end up getting, well, let's draw it up here. I end up getting a washer shape. This is not a cylinder because a horizontal line moved around horizontally makes a flat disc with a hole cut out, a washer shape. So this is actually a washer. So remember that then we say, well, if it's a washer, that's pi r squared minus pi r squared, where big R is the radius of the big circle and little r is the radius of the small circle. So far so good. What is the radius of the big circle? Now we have to be a little careful because we've got this extra x equals -3 that we're rotating around. The radius of the big circle is going to be the height of the function. Okay, well, let's ask one other thing. At this point, what is our variable? Based on our horizontal line segments, we move these horizontal line segments vertically to fill out the region, which means that y is the variable. And if y is the variable, well, then I need y as the variable, which is already given right here. Y is our variable in the way that's written. We need to know what are the y values for the limits of integration. This is y equals 0, and this is whatever I get when I plug 2 in for x. If x is 2, right, if x is 2, then I have to plug 2 in for x, and I get y squared plus 1. So I get y squared is equal to 1, so that y is equal to 1. So we may have to do some solving to figure out our limits of integration depending on what the variable is. Okay, so that's good. So my limits of integration in my final answer are going to be y equals 0 to y equals 1. Now we want pi r squared minus pi r squared. The radius of the big circle, this big circle that I've drawn, the radius of the big circle is this function height plus 3. Right, so I like to draw these pictures out and think about it like that. If you look in the book or some examples, you might see something about curve minus curve, right? Top minus bottom is what we've seen a bunch in almost all those situations. And you can think about it like that. Function minus -3 if you want to do that, right? Top curve is the function, bottom curve is -3. I'd rather just draw the picture and say that the total radius is the function height plus an extra 3 because we've moved to the left in our rotation. So it will end up being pi, the big radius will be the function height, which is this function here, y squared plus 1, plus another 3. So that's pi r squared minus pi times the little radius squared. The little radius in this case is always 3 because these are the straight, this is the y-axis, this is 3 units here, this is 3 units here, this is 3 units here. So the little radius is always 3 because we've moved 3 units to get over to here. So that will be 3 squared. Y is my variable. And we're done. Okay, one more. Okay, let's take y equals e to the x. And let's go from, let's take this region right here. And let's go around the y-axis. Okay, that's our plan. We want this region, we want around the y-axis. So the questions always in order are vertical or horizontal line segments. And this is one of those situations where it doesn't matter. Because if I have a vertical line segment, it's straight line to curve, straight line to curve, straight line to curve, the whole way down. One line to the curve, so it's just a single region. If I have a vertical line segment, or a horizontal line segment, it's axis to curve, axis to curve, axis to curve. So regardless, we would not have to break the region up into two different regions, whether we use a horizontal or a vertical line segment. Let's actually use a vertical line segment here for a couple of reasons. We'll see that it'll lead to shells, which we need more practice on from this section, but also because when I use a vertical line segment, that means that x is the variable, and if x is the variable, that's the way it's already written right here. So I don't have to rewrite anything. But if you don't see that right away, that's okay. Because as long as you notice that you can use either horizontal or vertical and go from there, you'll get to an answer that is correct. So we're going to use a vertical segment, which means that x is the variable. Which does mean that we need to do one thing here, right? If x is the variable, I need to know what this point is. I need to know what that is. But if y is 4, that means that 4 is equal to e to the x, which means that ln 4 is equal to ln of e to the x, which is x ln e, which is x. So x is equal to ln 4. So this is ln 4. So my limits will be x equals 0 to x equals ln 4. What happens when I rotate this around the y-axis? If I take a vertical segment and rotate it around the y-axis, then I end up getting a cylinder shape, which means that we're using shells. So we're looking at 2 pi RH as our formula. X is the variable. X is going from 0 to ln of 4. 2 pi is 2 pi. R, the radius in this case is always, well, not always, but because we're just rotating it around the x-axis, we don't have any extra 3 units like we did in the previous example. But the radius of this is really just where we are, our position. Our position here is just x. And then that varies as we move across the region, but the radius is x. And the height, this is the one where we have to be a little careful. The height is not the function. E to the x is not the height of the cylinder. E to the x is the height to here. What we actually need is the total height of 4 minus the function value. This is 4. This is e to the x. So the height is 4 minus e to the x. Two pi r h integrated with respect to x. And that's the answer. And there we have it. That's a few more examples of these, of shells, and then sometimes disc washer, depending on the setup. And I'll see you next time.